Hey everyone, in this dimensionless number video, we're going to be diving into what the Prandtl number is. We'll explore its significance and discover its wide range of applications. So let's get started. The Prandtl number is a dimensionless number and it plays a critical role in fluid dynamics and heat transfer. But what exactly is the Prandtl number? Why is it so important and why do we learn about it? Firstly, the Prandtl number is often represented by PR or a capital N with a subscript PR. It is a dimensionless number, meaning that it has no units. Dimensionless numbers in engineering provide us a convenient way of talking about situations where there are multiple coupled transport mechanics. The Prandtl number is described as the ratio of momentum diffusivity to thermal diffusivity within a fluid. This means that the Prandtl number compares how the fluid transfers momentum to its ability to transfer heat through the fluid. Expanding out these two terms, we get that the Prandtl number can be written as the specific heat of the fluid times the dynamic viscosity of the fluid over the thermal conductivity of the fluid. I'll just take a second here and write out all these variables for you so that you can understand them more easily. Before we get into some examples of using the Prandtl number, I just want to clarify further that we use the Prandtl number to describe a fluid's momentum and thermal transport mechanics, meaning from this number we can understand how it will behave when both momentum and thermal transfer are present. Now, let's look at three plates wherein we have a fluid coming in contact with a solid plate that is at a different temperature than our fluid. Therefore, we'll have both momentum and heat transfer. As the fluid hits a plate, the momentum and temperature about our plate is going to influence how the fluid behaves. These lines here represent what we call boundary layers, which demonstrate transport gradients. When the line straightens out, you can think of that point as where our fluid is at 99% of the free stream property, meaning that it is practically the same conditions as the air completely unaffected by the plate. Then, within our boundary layer, we have some gradient of that property. In our first plate here, we have a very low Prandtl number. This means that the thermal diffusivity of the fluid is dominant over the momentum diffusivity of the fluid. And with the higher thermal diffusivity, this means that the temperature influence of the plate will propagate out further from our plate through our fluid. On the other end of the spectrum, with a high Prandtl number, the momentum diffusivity of our fluid is now dominant, meaning that the fluid transfers momentum much better than it does heat. Therefore, the influence of the momentum in the fluid will be felt farther away from the plate and induce a physically larger hydrodynamic boundary layer in which the gradient will be more spread out. Just to reiterate that the Prandtl number is a number that is specific to a fluid and has nothing to do with the matter, such as our wall here, that it is interacting with. Additionally, the Prandtl number is a function of the fluid's pressure and temperature. Now that we have an understanding of this dimensionless number, let's imagine two practical examples, in which we have two different fluids flowing through heated pipes. In the first example, we have a viscous fluid called ethylene glycol, and it has a rough Prandtl number of 165 at 25 degrees Celsius. And into our second cylinder, we have air at 25 degrees Celsius also, and it has a Prandtl number of 0.7. Let's imagine that both these pipes are heated to 100 degrees Celsius. Assuming the same inlet velocity, take a minute now and try to figure out what the boundary layers of these two fluids will look like as they travel through the pipe. Let's begin by looking at our ethylene glycol example first. In this example, we have a high Prandtl number, meaning that our momentum diffusivity is going to dominate the thermal diffusivity. Therefore, a hydrodynamic boundary layer is going to develop much faster than our thermal boundary layer. We could represent our temperature gradients in this drawing as well. As you can see here, I drew out our velocity and temperature gradients at equilibrium, but you could draw them earlier in the pipe as they would just be less developed, and it would look something like this. One thing to keep in mind here that we talked about briefly is if the incoming temperature of our ethylene glycol is increased to say 90 degrees, then our Prandtl number decreases to 29. This is due to changes in the fluid's viscosity and thermal diffusivity. In our second example here, we have air flowing into our heated cylinder. Since we have a Prandtl number less than 1, our thermal diffusivity is going to be slightly more dominant than our momentum diffusivity, meaning that the temperature of the air will reach steady state faster than the fluid's in-stream velocity, which will reach a steady state later. Lastly, let's talk about some realistic ranges of Prandtl numbers. In practice, it is common for gases, obviously being very non-viscous in comparison to fluids, have very low Prandtl numbers, such as 0.6 to 1, whereas extremely viscous fluids have a very hard time with thermal diffusivity, and we can have Prandtl numbers that can be extremely high, such as 100,000. I hope that this video helped your understanding of what the Prandtl number is and how it is used and can be useful in studying fluid mechanics. If you enjoyed, please like, subscribe, and consider checking out our YouTube memberships by clicking that join button down below. However, if you have any comments, questions, or concerns about the information I provided in this video, please leave a comment down below and I'll do my best to address your concerns.